So we've spent plenty of time now studying differentiation in multivariables. So now it's time to move on to the other aspect of calculus, which is integration. Right? And since we're dealing with functions of 2 or 3 variables, the domain we have to integrate over now is no longer just an interval. It's actually some region in the plane or some solid in 3D space. So we'll start with just talking about the region integrals over a region in 2D space. So for functions of 2 variables. But before we start that, let's take a quick look back and remind ourselves how we define the integral for 1 variable. Okay? So if we have a function, say this is the y-axis and this is the x-axis, and we have some function y equals f of x here, right? And we want to integrate that from, actually let's use solid lines here, from A to B. How did we do this? Well, if you remember, what we did was we cut up the base here, this interval A to B, into a bunch of tiny pieces. Right? And I'll do some dots here. Right? And we cut it up into small pieces, and each of these has length delta x. Right? And how many pieces are there? There's n pieces. Right? So n subintervals. All right? And then we label these points as, well, we don't need to worry about that. All right? And then what we can do is break this area into a bunch of little columns. All right? So remember, you might have, of course, some columns in here, but let's do some dots around here. All right, just to say, there could be, we don't know how many is divided up in there. All right. So we divide it up like this. Then what do? The next step is to take inside each of these subintervals, take a point in here. So call this one x1, x2, and then inside each of these, and eventually we get xn, xn minus 1. Right? So we have kind of sample points inside each of these, and then the way we do the integral was by approximating the function by rectangles. All right, the area under the function by rectangles. So what does that look like? Well, what that ends up looking like is, so we evaluate the function at each of these sample points. So that gives us points like up here, up here. Actually, let's use green here. Right? And then we make rectangles with that height. Right? And they split according to our intervals here. Right, so at the end of the day, you'll see something that looks like this. Right? So we approximate the area under the curve by a bunch of rectangles. And I know this is getting a little sloppy here, but right? And then the integral, finally, was approximated by just adding up the area of those rectangles. So the area was about the sum from I equals 1 to n of the area of this rectangle, which would be f of xi times delta x. Because f of xi up here gives us the height of the rectangle, delta x gave us the width. All right, and then we got the actual area by doing a limit as n goes to infinity. Also remember here, delta x was b minus a over n. Okay? So we got the actual area by doing a limit of this sum. And then we called that the integral from a to b of f of x dx. Okay? So if you remember, that's how we found, or we set up the integral to integrate a function. All right? So how do we do this now in two variables? Well, we have to come up with an analogous Riemann sum. So we're going to erase this board, and then we'll go on. All right. So now to define the double integral, we're going to, let's think first about what it looks like geometrically. Right? So let's first assume that the function is always positive, just like you had to do with the single variable integral. Right? If you graph a function, say z equals x squared plus y squared plus 1, right? That's a paraboloid that's lifted up a little bit. If we integrate that over a square in the xy plane, what that's going to tell us is the volume of the solid that lies above that square but below the paraboloid. So you might imagine, instead of using rectangles to estimate area, now we're going to use kind of rectangular columns, if you will, to estimate volume. All right? So how do we set this up? What does it look like now? So let's say what we're trying to do is this. Integrate f of xy over the rectangle r equals ab cross cd. Right? So that means, x goes between a and b, and y goes between c and d. All right. So how do we do this? All right, so it's a little bit harder to draw the full 3D picture here for you. So in the next video, we'll show some Mathematica showing these columns estimating the volume and so on. But for now, let's just get the definition out of the way so we can get past the Riemann sums. Okay, so how do we do this? Well, the idea is again to divide this region of integration into a bunch of little pieces. All right, so let's say A is here and B is out here. Oh, and C is here and D is up here. All right? Then that rectangle looks like this. Something. All right, so here's the rectangle R. Right? Now, what we need to do to this is cut this up into a bunch of pieces like we did before. All right, so let's say we cut it up something like this. All right? So we can do that. Right? And what I want to do is so that each of these in the x direction and in the y direction should have delta x length. All right, and in the y direction, the height of these rectangles here should have delta y. All right? Okay, so now hopefully you remember the next step is we choose a sample point inside each of these. And just like you did in Calc 1, I believe, with these, and I think a little bit in Calc 2 as well, you could pick things exactly in the middle of each rectangle and get the midpoint rule. You could always choose things from a certain corner. It's a little bit harder to say, left end point, right end point. You can do things based on corners now, but again, since we're not actually going to do anything computing these in class, we'll just stick with just defining the Riemann sum. So that just means we just have to pick some point inside each of these, just some sample point. And it doesn't matter which point, right? So also another thing I want to point out is here in the x direction, I know I've only drawn 5 here and 3 up here, But let's say this is in m pieces, and this one is in n pieces. Actually, we don't need the dash here. All right? So we cut the x direction into m pieces and the y into n. All right? And then, we can say this is the first interval, the second, the third, fourth, fifth, and so on. So what that allows us to do is say this point right here would be x. I don't want to draw too tiny in here. So what I'll do is come up here and just draw an arrow to that point, and we'll call this xi, yj. All right? And that means it's in the ith rectangle counting from the left, and the jth rectangle counting from, I guess, the bottom here. And it actually won't matter which one, but let's do it that way. All right? So now, those are our sample points. All right, so now it's pretty much directly straightforward from what it was before. Right? Over each of these rectangles in the bottom, we have to construct sort of a square pillar now. And what should the height of that pillar be? Well, hopefully you might guess it's f of xi, yj. All right? So that means the area is approximately the sum from, I guess let's say I equals 1 to m, and the sum from j equals 1 to n of f of xi, yj, delta x, delta y. Okay? And, well, what we'll call delta x times delta y, we'll call that delta A, right, for the area of the rectangle, right? So we'll leave that off here. Right? We'll just say this is also delta A. All right, and well, what was the next step to get the precise area under the curve in one variable? Right, you might remember it's the limit. All right, and we took, the limit is the number of little subdivisions went to infinity. But now notice here we have two ways we're cutting up. So there's going to be two limits. So the area precisely is given by the limit as m goes to infinity and n goes to infinity of the sum I equals 1 to m, sum j equals 1 to n, f of xi, yj, and this time I'm just going to do delta A. I'll leave off the delta x, delta y. Right? And this thing right here, this is what we call the double integral of f of xy dA. Right? And we say we integrate over this rectangle R. So we just put a little r down there. Right? So that's the main idea that's the main idea for setting up the double integral. Right? It's the same process we did for single variable, except now there's an extra direction to worry about. And you might guess that nothing much changes when you go to triple integrals, which we'll do in a few videos, but you'd be right. There's really not much difference. There's just an extra sum and an extra variable and an extra limit. No big deal. Right? So this is the definition. And let's clear this up and then set up, how do you actually go about computing this? What does this look like?
All right, so we just want to go through here real quick in this Mathematica demonstration to see sort of what a Riemann sum looks like, since it's really hard to draw them by hand in 3D. So here's basically the simplest function, a constant function. This one is z equals 5, or f of xy equals 5. Right? So this is what the Riemann sum basically looks like here. Again, you just see a bunch of these pillars, right? And it's approximating the volume under this sheet, z equals 5. All right, well, that one's a pretty simple function. So let's go to something a little more complicated, which is 4 minus 2y. All right, so here you can see something like we had before with Riemann sums. We're trying to approximate the volume underneath here using a bunch of rectangular columns. But as you can see, it doesn't quite fit the volume exactly. So what we do is, well, we increase the number of partitions in each direction. And now you can see after doing that, it's starting to fit the volume a lot better. And then if we expand it as far as this will go, we can see, you know, it's getting a lot closer. Okay, so let's bring these back down real quick to here, and let's switch to the next function, which will be x squared plus y squared, the paraboloid, or a piece of it anyway, right? So keep in mind, in this video here, we're integrating over the rectangle, what is this, 0 to 5 cross 0 to 5. Okay, all right, so now this time, right, again, we can see it's missing quite a bit of area. So if we up the number of rectangles, we can see that it changes here, right? And then, yeah, so then we can also move where the sample point is chosen inside the little rectangle that these columns are over, right? And you can see, you know, that changes the type of approximation here, right? So let's go to one more function here, which is y sine of x, y times sine of x, right? And again, you know, we can see we're trying to approximate the volume using these columns, right? And once again, increasing the number of them just makes the approximation better and better. So if we make both, or if we send both delta x and delta y to 0, which means we fill this up with an infinite number of really, really tiny columns, we get the exact volume.